So let's go to the 2.2 notes in the very last problem, the one about the rows of seats in the theater. Would you agree that's where we're at? Is everybody good? All right, so here we go. The fifth row has 31 seats. So since it says it can be modeled by an arithmetic sequence, I'm just going to say a sub 5 is 31, and a sub 11 is 49. And I am going to determine how many seats there are in the 25th row. So does that make sense to you? All right, so what's some strategies? What are some strategies that we can use here? There's lots of ways you can process this. What do you think, Josie? So Josie says, if I think of this as a sequence, the 5th term and the 11th term are separated by a total distance of 18. And the difference of the terms is 6, so there'd be 6 steps I would take in there to get from 5 to 11. And a total distance of 18, so my common difference is 18 divided by 6 or 3. Does that make sense to everybody? Now you can also take a formula approach to this. I mean, that's fine, 100%, that's fine. But you can also take a formula approach and say, well, 31 equals the first term plus the difference times 4, because it's the 5th term, and minus 1. And 49 equals the first term plus the difference times 10, and you can solve that system. That will always work also. We talked about that yesterday. This is fine. What she did is absolutely great. All right, Josie, so now I know the difference. Okay, what do you want to do now?
Subtracted 3 from the 31, like 4 times.
Absolutely, so just back, that will work. Now I already have this written down. If I now know that D is 3, can't I figure out my first term? So my first term will be, did you get 19? So your first term is 19. So Josie did it by simply subtraction, multiple subtraction. I can do it with my formula. However you figure it out is right. The 25th term will be the first term plus the common difference times 24. So what is that, 72, 91?
Yes.
So 91 seats. All right with everybody? Again, lots of ways to figure that out. You can do it however it works for you. All right, let's look at Jerry's greeting cards. All right, so Jerry stocked 3 packages when she starts additional. Okay, here we go. What do you notice about the information in the table? Do you notice any patterns? So every half hour, we're stocking 35 more cards. Would you agree with that? So that's a constant rate of change. So we have an arithmetic sequence here. Would you agree with that? At what rate is Jerry stocking the packages? 35 every half hour or 70 every hour? That's probably the way we would say it, but it's the same thing. Either one is fine. Write an equation for the number of packages Jerry will have stocked X hours after her shift begins. All right, now you already told me that this is well, you didn't. You said it was linear, which means it's arithmetic, right? So I need a formula for the nth term, X hours, N hours. Well, call this arithmetic. Alright, so what do you wanna come up with here? What do you think you can come up with? What, Quinn?
I have something, I'm not sure if it's right.
Sure.
73 plus 70 and minus 1.
Or, we're gonna clean these up always, so that's gonna be, 70n minus 3, no, plus 3. So this is Quinn's. Can we check that? We talked about this the other day too. Absolutely you can check it, because don't you have some data points? So according to the chart, after 2 hours, I'm just picking a random number, after 2 hours, she should have 143 cards. So if I put 2 in here, do I get 143? I think you got it right on the money. Good job. All right, okay, that's that one. If Jerry has to stock 150 packages of cards, how long will it take her? Well, what are we gonna do? Put 150 in here? So 147 over 70? Check my arithmetic, is that right? So it's gonna take her about 2.1 hours? Or, since we don't normally say 2.1 hours, how else could we say that? 2 hours and 6 minutes? A tenth of an hour, 6 minutes? The greeting card industry is on the decline. In 2020, Americans purchased, okay, this number has continued to decrease, 2.8% per year. Uh-oh, wait a second. When they start talking about 2.8% per year, that's a decrease. Are we arithmetic anymore? No, now we are geometric. How many greeting cards were purchased in 2021? Okay, now, be careful, don't make this harder than it is. In 2020, we had 6.5 billion. And we wanna know 2021, isn't that just the very next term? And how do we get from term to term? Here it says, we decrease 2.8%. So what am I gonna multiply by? 0.978, or 972? Because if we're losing 2.8, we're keeping 97.2, aren't we? So all I'm gonna do is take 6.5 times 0.972. Remember, that's billions. Did you get 6.318 billion? Everybody on board? What is the ratio of greeting cards purchased from 2021 compared to 2020? That's kind of a silly question. Is it the ratio 0.972? Okay, number 6, complete the table. Well, we already did 2021. And it was 6.318. All right, how can we find the rest of these numbers? How can we find 2022? 0.972. 6.141. And then take that times 0.972 again. 5.969, okay. How about the other direction? How am I going to go backwards? To go to here, I times by 0.972. How am I going to go this way? Divide, so 6.5 divided by 0.972, 6.687, and then divided by 0.972, 6.880. Does anybody have a question about where those numbers came from? Is the number of greeting cards decreasing by the same amount each year? No. No. Xander, explain that. You're right. No.
Well, as like the numbers decrease and then, the percent stays the same, it's not gonna be the same because the amount is different.
The amount is different. So if you subtracted these two numbers, it would not be the same answer as if you subtracted these two. Does that make sense to everybody? If it were the same, the thing would be linear, right? So the ratios are the same, not the amounts. All right, write an equation for the number of greeting cards purchased X years after 2018. So we're gonna let X be the number of years after 2018. And Y is gonna be the number of cards, okay, in millions. Could we approach this as a geometric sequence? And Y would be our nth term. All right, so what do you want it to look like? What's our first term? What's our ratio? 0.972. All right, let's check it. According to the formula, let's see. This is the first, second, third, fourth, fifth term. So let's just say the fifth term, according to this, the fifth term should be, whoops. Let's check it and see if that's right. Might be a little off because of round off. Is it right? Yeah. All right, good work. Good work, good work, good work. Oh, wait a second. No. Something's not right. Can anybody see what's not right? If X, or what I call N, these are N's, if they are the years after 2018, is this really the first term? No. This would be the first term, right? So here's what I want you to stop and think about for a second. When I found G sub 5, that should be 5 years after 2018. It wasn't 5 years after, it was only 4 years after. So we're gonna have to modify here. How could we fix this? There's a couple ways we could fix it, but what's one way we could fix it pretty easily? Change the first term to what would be literally the first term, 1 year after, 1 year after, and so that should be 6.687. Now the equation does what we want it to do. Is everybody clear about that? Now it makes it so it's giving us the amount X years, N years after 2018. Okay, perfect. compare your expressions, what makes them different? Well, that's kind of obvious what makes them different. One's arithmetic and one's geometric. So one is changing at a constant rate and one is changing at a proportional rate. All right, check your understanding. You and your partner quickly, there's only 3 of these here. Quickly see what you can figure out in the check your understanding section. And I'll fix my attendance. Before we run out of time, we really need to talk about one of these. How about A? What did you get, or number 1, what did you decide about that one?
Linear.
You're on fire today. Yeah, it's linear. Now here is what I think may have confused some of you. Were you looking at your x's, you guys? Because remember, when you start looking at the differences, you have to consider how far apart your x's are. So if you look at the first 2 points in that chart, the x's differ by 2, and the y's differ by negative 6.5. So what is the actual rate of change? What is the actual slope? Negative 3.25. So then if you skip down and look at the 3rd to the 4th, now the x's are differing by 3, but the y's are differing by negative 9.75. Well, when you find that slope, it is exactly the same. So you cannot just look at the y's, you guys. You have to make sure. Okay, yes, you can look at your y's if your x's are evenly spaced. But if they're not, then you have to look at both. How am I actually changing? So that's linear. Is everybody okay with that? That's linear. All right, number 2. 2 points, write the equation of the line. Oh my gosh, you better have been able to do this. What did you do if you were making a linear function? 63 minus 7, which is, what is that? 56. Over 1 minus 3, 63 minus 7, 1 minus 3, negative 2. So negative 28. And then what? Y minus 63, or 7, maybe 7's easier, it doesn't matter. Y minus 63 equals negative 28, x minus 1. I'm writing a linear function though, so I gotta get y by itself, so I'm gonna go ahead and distribute. And my linear function is, does that look okay to everybody? My linear function, negative 28x plus 91. Okay, if you struggle with that, I need to smack you. This is just writing the equation of a line, right? It's the next one I want to talk about, because now we have to write the equation of an exponential. And we really haven't spent much time talking about what exponential functions look like. It's actually in section 2.3. So we kind of snuck this in here a little bit. An exponential is an equation of this form. This is an exponential. So you know how a line is of the form mx plus b? Well, this is the form for an exponential. So your job is to write an equation like that for these very same 2 points. Now, there are a couple of ways, always there's more than one way. But one way that you can do this is to take your point and put it in to your format. So this is the format for an exponential. So I know x is 1 and y is 63. And then do the same thing with this one. This is kind of what we were doing the other day, only this one's gonna work out nicer. Now, what do we have here? What is this? It's a system of equations. So solve it however you want. I like to, since they're both always gonna have an A, I like to just solve for A instead of equal. So 63 over B equals 7 over B cubed. You may or may not do the problem that way, but does that make sense? Is that right? So then I can cross multiply. What do I do now? You could actually divide by 7b if you wanted to. So you'd have 1 equals 9b squared. So b squared equals 1/9, which means b equals 1/3. One of the rules of exponentials is that b must be positive. So I know when I square root, technically there's a plus or minus, but not in an exponential. B must be positive. Now what do I do? Well, if b is 1/3, can I figure out a? So I'll just put 1/3 right here. Times by 3, so it looks like a is 189. So what's my equation? Y equals 189 times 1/3 to the x. Interestingly enough, you can write the equation of a line with 2 points. You've known that your whole life. You can write the equation of an exponential with just 2 points. It's kind of a cool thing. All right, anybody have a question about that? if you did that problem a different way, make sure this is what you came out with or some equivalent version of that. Okay? All right. Okay, let's do number 3. Did you get this far yet? A geometric sequence has a common ratio of 4, and the second term is 24. Which of the following could be used to generate the terms of the sequence? Anybody having a thought on that? Couldn't even full of great ideas today. Did you ever thought on that? Yeah.
Not yet.
Not yet.
If you generate one.
A sub 2 is 24. The ratio is 4. Okay. So what do you think it is, Quinn?
Maybe D.
D, an exponential function with a y-intercept of 6, a constant proportion of 4, and a domain of all real numbers. Okay, I'm gonna stop right there and say no. Because domain is which letter? X. And this is what an exponential looks like, right? Domain of all real numbers is fine here, but this is a sequence. This is a sequence. Can X be 1.5 in a sequence?
No.
Can you have the 1.5 term?
No.
No, in a sequence you have a first term, second term, third term. What's your domain in a sequence? The set of whole numbers, right? The set of whole numbers. So it can't be D. Could it be C? Positive integers. Could it be C? Well, if the second term is 4 and the ratio is 2, if the second term is 24 and the ratio is 4, what's the first term?
6.
6? So your sequence would be, your geometric sequence would be a sub n equals 6 times 4 to the n minus 1? Right? So if we put 1 in there, we get a sub n equals, or a sub 1 equals 6 times 4 to the 0th. So there we go. There we go. Oh wait, no, I need a y-intercept. Oh yeah. So if I put a 0 in there, I need y-intercept. So if I put a 0 in there, is that gonna give me 1.5? 6 over 4. Yeah, there we go. Yep, that one works. So it is C. Thank goodness, we couldn't have been together. All right, let's quickly look at the next page. We're not gonna have time to get very far in here, but at the very top, Mr. Passwater has spent way more time with all these tests than I have, for sure. And he says that on the SAT, ACT, and certainly in AP, the main types of functions that show up over and over and over again are these linear, quadratic, and exponentials. So linears, we spent a lot of time with, quadratics, we spent some time with, and now we're gonna start looking at the exponentials, which are of this form right here and have that shape. That's what an exponential looks like under normal terms. Obviously, if you put a negative in there, you can turn it upside down. If you put pluses and minuses in there, you can move it around, but it has that general shape. All right. Key characteristics of exponential functions. Okay, so we got the form. I've already told you B has to be positive. the A in the equation, in the format, A represents the initial amount. So these are gonna be used for populations, for bank accounts, for the amount of an element after, with a certain radioactive decay constant. A stands for how much you start with. B represents what you're multiplying by, or the constant of proportion. So in geometric sequence terms, B is R. It's what you multiply by. So in our reading card problem a minute ago, what was our B? 0.972. That's what we kept multiplying by over and over again. All right, I'm gonna stop there, because we're out of time, and I want you to get your stuff put away, please.
Pardon this interruption. This is just a reminder to leave all backpacks and coats